Okay, welcome to another operations research video. This is the introduction to simulation video. So simulation is a pretty powerful tool for when you're dealing with stochastic systems. So any sort of system where the system evolves over time probabilistically. So it's not deterministic. You aren't guaranteed exactly what's going to happen in the future, but instead you look at some random chance playing into it, and you're looking at the probability that it's going to be in a certain state in the future. Okay, so some examples of stochastic systems that we'd like to model in operations research include queuing systems, which we'll also talk about this week, inventory management, right? Uncertain demand from day to day, and how do you keep enough stock on hand to meet those demands without carrying a bunch of extra stock that incurs extra costs. Reliability analysis, if you're running a plant for example, manufacturing, and you've maybe got some redundancy built into your system, of maybe you got two machines that can do a certain job or work. What's the likelihood that both of them go out of commission at the same time, right? And kind of grind everything to a halt. And so if you want to sort of analyze the probability or the chances of things like that happening, simulation can be helpful. You can simulate financial systems and kind of look at different risks associated with that. Also, pretty common to use simulation for forecasting. So you can kind of simulate future outcomes to kind of get a sort of a cone of possibilities of what might happen in the future based off of your forecasts. So those are just some of the examples of stochastic systems where chance plays a role in what will happen next, but there's many more. And so we're going to talk a little bit about simulation in this video. Next video, we'll have an example of simulation. When we move on to talking about queuing systems more this week, there'll be examples of simulations in those as well. So most simulation models are built on the following building blocks. And so if you can kind of ask yourself these series of questions, then you're most of the way to building your simulation. The first building block is the state of the system. What information do you need to know to kind of have a snapshot of the system and then predict what's going to happen next or what could happen next, okay? So for example, in queuing systems, the state of the system is mostly how many people are being served and how many people are in the queue at a given time. For inventory management, it's probably how much inventory do you have on hand, as well as maybe any information that you have about orders coming in. For reliability, the state of the system is probably which of those components are currently functional and which of them are needing repair and which ones are being repaired. Similar sort of things for kind of financial analysis and forecasting. They sort of have different states that you might be interested in tracking over time. So once you've sort of defined what the state of the system is, then you want to define what are the possible states or possible values that state could take. So how many people could be in the system, or how many, what are the different values that it can take on? And then you want to identify what are the possible events that can take you from one state to another state. For example, in inventory management, a customer showing up and buying one of your products, that reduces your inventory, so that changes the state of the system. Or an order coming in with more of that product is another event that changes the state of the system. Okay, so you want to kind of think of what's the state and what are the things that can change the state? What events do I need to essentially simulate happening that can cause changes to the state? Most simulations have some sort of simulation clock. I put that loosely because not always are you simulating something over time, but maybe you're simulating it, a bunch of things happening in parallel maybe. But usually there's some sort of clock, and it can either be a continuous clock that kind of you simulate how much time till the next event, and we'll see that as an example when we get into queuing theory. Or it can be a discrete, where essentially you simulate one day, and then you simulate the next day, and then you simulate the next day, and sort of each day is separate, and that makes it nice and easy to kind of move forward to the next unit of time. You need to have a method of generating those random events that can change the state of the system. And so having some working knowledge of probability distributions will be useful. And then when you generate those events, you need to identify, okay, how does that change the state of the system? For most simple systems, it's pretty kind of straightforward, but sometimes it's not 100% straightforward. And so, yeah, these are the building blocks for most simulation models and sort of the questions that you want to ask. As you get familiar with more and more simulations, the kind of easier this becomes. But first time through it, there might be multiple ways of kind of defining the state, and it might not be obvious which one's the best way to define the state. And to be honest, sometimes I'll try something, I'll realize that there maybe was a better way, and kind of redo or rebuild my code after the fact. Okay. And one thing I'll emphasize is, so simulation kind of tells you what can happen, and then you repeat it many times, and then you know sort of what can happen on average, or sort of what can happen worst case, or what can happen best case, right? But then oftentimes outside your simulation, you've got some policy decision that affects that simulation. So you maybe have some design choices over the system, and you sort of set the design decisions, then you simulate what's going to happen, and then you sort of loop through the different possible design decisions, and each time run a simulation to see what will happen. And that can help you pick out what are the best design decisions or policies for that stochastic system. Okay, and we'll see an example of a simulation where we're going to do that. So these are the building blocks. One of those building blocks is generating those random events. So let's talk a little bit about generating random values in R. Probability distributions are going to come into play whenever you're generating random numbers. And if you want to know a little bit more about what distributions are available in R, you can type in !distributions, and that will open up the help file for the distributions in the stats package. So I'll pull those up over here. And if you scroll down, it's got a kind of list here and links to the help files for the individual distributions. So the beta, the binomial, the Cauchy, chi-squared, exponential, F distribution, gamma, geometric, hypergeometric, log normal, multinomial. Yeah, so I'll be honest, some of these I've never actually used in practice, but some are very, very useful. Okay. And the thing to know about R is R sort of has a sort of standard way of dealing with most of these distributions. You'll notice that these help files have links to the D and then name of the distribution. And so so for the gamma distribution, they've got a link to the D gamma function. For the F distribution, it's the DF function. And for exponential, it's D exponential or DEXP. Okay, so each of these distributions has a function that will compute its density. You can think of the density as sort of the likelihood of being at a certain value. The P function, where it's going to have P followed by the name of the distribution, is the cumulative distribution function. So the probability that you'll see a value less than something. Okay. The quantile function, which is the opposite of the cumulative distribution function, where you give it a probability and then it will give you the value where the probability of being less than that is equal to the probability that you chose. But the one that we're most interested in when we're doing simulations is the R function. So R followed by the name of a distribution generates random numbers from that distribution. And so if we're doing a simulation, we're not so much interested in finding out about the distribution, but generating values from it. Okay. So I encourage you to pause the video, open up the linked R Markdown file. Let's generate 10,000 observations from one of your favorite distributions. Okay, and I'll talk a little bit more about some commonly used ones, but you can kind of scroll through here and let's look at Poisson first. You'll notice here are the four functions that deal with the Poisson distribution, as well as what are the arguments. For these R functions, usually the first argument is always the number of random values to return, okay? And so here I'm saying generate 10,000 observations. And then the second thing is most distributions have some sort of parameter that controls the shape or location of that distribution. In this case, Poisson distribution has a parameter called lambda, which is its mean value. In this case, I've got lambda equals 3. And if I do that, I get something that looks like this. So Poisson distribution is a discrete distribution. So it takes on kind of whole number values and positive whole number values, actually. And so here's the probability of 0, or here's a histogram of a bunch of repetitions. And we can see how many of those repetitions had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 events happening. Okay. But you can also use a different distribution. And so I encourage you to play around with a couple. So you maybe some to draw attention to would be the uniform distribution. And so R unif, I'll need to give it its min and max. So R unif, I'll still generate 10,000. I don't need a lambda, but I need a min equals, well, you could also leave them at the default. So if I look in here, the default value for min is 0 and the default value for max is 0. And actually, the most common uniform distribution that you'll generate is the uniformly distributed between 0 and 1. And if I do that, here's a histogram of all the values. A uniform distribution gives equal probability to every value between the min and the max. And so here we can see there's roughly about 500 observation in each of these little rectangle bins that look like they've got increments of about 0.05. So yeah, that's a uniform distribution. Play around, find a couple other ones, look at their interesting shapes if you plot a histogram of them. Okay. Let's talk maybe about some commonly used distributions. So most distributions are split up into continuous distributions that can take on decimal values, all the intermediate values between numbers, between whole numbers. And so some common ones would be the uniform distribution that generates uniform numbers between a min and a max. That's what I just generated up here. It's really valuable in generating sort of other distributions, is that you can kind of take your uniform between 0 and 1 and then transform it to get some more exotic distributions. I'll show you a little bit in the next video how you can use it with a case when to create custom categorical or discrete variables where you have sort of some probability, you know the probability of each of the outcomes, and you have a finite number of outcomes. Okay. Normal distribution is a very common distribution to deal with. It's your typical bell-shaped distribution. It's specified by its mean or average value as well as its standard deviation. Excuse me. The exponential distribution is a very, very useful distribution in queuing theory. It is a continuous distribution, always generates positive values, and it's commonly used to simulate the time between events. And so especially if you're doing anything with a continuous time clock, where you need to move forward to some next event that's maybe some amount of time in the future, but not a fixed amount of time in the future. You can use sort of an exponential distribution to do that. Really, really powerful for queuing systems, and we'll have a lecture just on exponential distributions when we talk about queuing theory this week. Some examples of discrete distributions is binomial and the Poisson distribution. Binomial is really useful if you're looking at the number of successes in a fixed number of trials. And so let's say I shoot 10 free throws, right? You could use a binomial model to simulate how many of those I made, okay? On the other hand, a Poisson is the number of events in a fixed period of time. And so maybe I've got people coming into my shop, and the fixed period of time is 1 day, and I want to simulate how many people come into my shop each day. A Poisson distribution would be a great way to do that. Okay. Also great for how many units did I sell in a day, or questions like that, where it's not a binomial because there's not maybe a certain number of trials that's fixed, but there's sort of a fixed period of time, and then a number of events happen in that time according to some rate. Okay, so those are some really powerful distributions and commonly used distributions when you're dealing with simulations. Okay. Now, if we're going to do a simulation, one of the big things we're going to need to do is loops. Okay, so you can run something once, and that can show you what's possible. But really, the reason why we want to do a simulation is because we want to run it many, many times to show what's probable or likely, or to compute an expected value. And so we're going to be using loops in these simulations. I've got a tip video just on loops. But yeah, typically we want to do at least 1,000 repetitions, depending on how computationally intensive each individual simulation is, kind of determines how many you're willing to do, right? If what you're trying to compute takes very little time per simulation, then you can do lots of repetitions. If each individual trial is very expensive, takes 10 minutes to run, you probably don't want to do 1,000 repetitions. Otherwise, you'll have to leave it running overnight. Okay. So kind of there's always a trade-off. The book has a nice section on sort of managing that trade-off of how many simulations or repetitions of a simulation do I need. And so I encourage you to kind of read into that chapter. Yeah, and so sometimes it's not important to worry about because each simulation is very cheap. But when each simulation takes a lot of time, then you want to be careful about how many repetitions you're doing. And then at each repetition, usually we want to record the important results from that simulation. And so usually there's some metrics that we want to record for each simulation we run. So these can be kind of like costs incurred during the simulation, or values that we're interested in. And usually we're going to want to store those in a data frame. And I'll show you how to do that in the first example down below. And then the other thing is that often outside the simulation loop, we're going to also be looping through policy choices. Okay, things that change how the simulation runs to then hopefully narrow in on what is the best policy choice, right? How much inventory should I aim to have on hand? Or how many servers should I have in my queuing system? And we can kind of run the simulation with a certain inventory level or a certain number of servers, and then repeat that simulation with a different number and see which one gives us better metrics, depending on which metrics we're interested in optimizing. Okay, and so oftentimes the optimization happens by looping through that policy, and really in most cases we have sort of a finite number of policy options, and we can just simulate each of them and then choose the best, is usually how the optimization is done. when it's related to simulation. But there's also other strategies as well that the book mentions. Okay, that's sort of an overview of simulation. The next one, we're going to do an inventory management example and kind of walk through one whole example. And I'll kind of show you how I build things up. I don't jump straight into coding a full study, but I usually start with kind of making sure I can make one simulation work, and then I do some repetitions of that simulation, and then I build the policy loop around that as well. So that's it for this video. I'll see you in the next one.